This slide shows the formation of deuterium, tritium, helium-3 and helium-4. The electronic orbits shown by thin lines are defined by the overall shape of the proton. At the bottom of the slide, the derived rules of building the heavier atomic nuclei are illustrated. They will be discussed later. This slide shows two rows of the periodic table. When the number of protons increases, the valence initially increases and then decreases, ending this trend at the noble gas. The positions of all electronic orbits are defined by the near fields of the protons and neutrons, so they are easily identifiable. At the right side of the second row, a mock-up of the argon nucleus is shown. This slide shows a comparison between the electron microscope images of gold layer and synthetic images using the BSM-SG models. The interatomic distance between the observed and synthetic image match very well. In BSM-SG models, it is based on the derived size dimension of the proton. This slide illustrates the types of nuclear binding between protons and neutrons, the derived building rules, and the nuclear shape tendency for the heavier nuclei. For derivation of the building rules, analysis of experimental data from different fields is used. It is apparent that the nuclei of stable isotopes are highly symmetrical. The electronic orbitals are strongly defined by the near fields of the proton. The magnetic fields of the electrons interact with the magnetic fields of the rotating neutrons. This causes a complex gravitational mode of magnetic field. If the total energy of this magnetic field plus the kinetic energy of electrons exceeds the supergravitational field, the nucleus decays. This slide shows the nuclear structure of some selected elements in two projected views. The polar axis and the tendency to rotational symmetry is apparent. This slide illustrates the classical explanation of the nuclear spin. The simple case of deuterium is illustrated. The rotational freedom of the neutron over the protons means that it can create a magnetic field. Combined with the magnetic field of the orbiting electron, the compound field may interact with the magnetic field of rotating proton. Rotating in the same or opposite direction, they provide two separate lines in the nuclear magnetic resonance. In heavy atomic nuclei, the magnetic field of rotating neutrons interact with the magnetic fields of the orbiting electrons, creating different spin states. The electronic orbitals of lower shells are aligned as illustrated by red lines in the nucleus of nickel. It is apparent from the BSM-SG atomic models that the electrons of the external shell define the fractional spin number. This slide illustrates how the near proximity electrical fields of protons and neutrons, shown in a gray color, define the Coulomb barrier of the atomic nucleus. It is interesting to see the configuration of the neutral atom known as Rydberg state. In the Bohr model of hydrogen, shown at the upper left corner, there is not a change of the shape of the electronic orbit between a normal and a Rydberg state. In BSM-SG models, however, there is an apparent change. In the normal hydrogen, the electronic orbit always passes through the hole of the proton. At the Rydberg state, it is outside. In this case, the large magnetic moment of the electron becomes detectable. I often call this state an ion-electron pair. At the lower left corner, a cluster of Rydberg atoms is shown. This cluster has a significant detectable magnetic field. This is important for understanding the physics of some low-energy nuclear fusion reactions. This slide illustrates an example of interaction between the magnetic moment of a Rydberg hydrogen and the magnetic field of the nickel nucleus at particular nuclear spin state. Such interaction could lead to overcoming the Coulomb barrier and obtaining a fusion reaction. The electronic orbits that might be involved in this spin state are shown in a red color. Such interaction will lead to a fusion of the proton at the polar nuclear region of a proper selected isotope of nickel. This type of reaction for two nickel isotopes is experimentally reported by Focardi and Rossi in 2010. Using the derived factor of the supergravitational field, denoted as CSG, a useful method is derived for estimation of the change of the center of mass as a result of fusion of a proton or deuteron into a heavier nucleus. The necessary input data are the atomic mass number and the released energy as gamma quant. The method is described in details in my book Structural Physics of Nuclear Fusion. This table illustrates the application of the derived method. It helps to predict some cold fusion reactions with a lack or minimal radioactive waste. The selection of the isotope number of the heavier isotope in this case is important. The method is described in this book. This slide illustrates a graphical modeling for analysis of some experimentally obtained nuclear reactions. This slide illustrates a possible interaction between the hydrogen in a Rydberg state and the lithium-7 and obtaining a lithium-6 isotope by release of a slow neutron. This corresponds to the experimentally observed effect known as a neutron spallation from lithium-7. Now let us show the application of the BSM atomic models in other fields. This slide shows a graphical modeling and analysis of some simple molecules. At the lower left corner, it is shown one unknown so-far state of the water molecule corresponding to the experimentally discovered brown gas, known also as HHO gas. The analysis predicts that this state may contain a higher quantum energy, so the gas has a higher stored energy in comparison to a mixture of hydrogen and oxygen gases at the same volume, pressure, and temperature. BSM-SG atomic models can be successfully used for analysis of nanostructures. The four valencies of carbon atom are defined by the two pairs of deuterons embedded in the carbon nucleus, positioned in two orthogonal planes. The analysis of electron microscopy of graphene single sheet confirms this feature of the carbon atom. This slide illustrates the fractal building of silver nanoparticles. At the upper left side, the experimentally observed nanoparticles are shown. At the lower right side, the fractal building using BSM-SG models is shown. Silver nanoparticles have antibacterial properties due to their average charge of 2 positive charges. The average loss between 1 and 3 electrons in their apexes is independent from the size of the fractal structure. The analysis with the BSM-SG atomic models envisions the existence of energy storage mechanism in some amino acids and biomolecules, a feature that is experimentally observed. This feature will be discussed in details in my plenary talk. In a recently published article in a peer-reviewed journal of biometrics and biostatistics, a few hypotheses are discussed about the Leaventhal paradox, the C-value paradox in DNA, and the decoding mechanism behind the 20th flavors of the aminoacyl tRNA synthetases. The BSM-SG atomic models are separately published as the Atlas of Atomic Nuclear Structures. In this slide, the models for all atoms up to the Z number of 102 are shown as a periodic table of elements. The protons and neutrons are shown by simplified symbols. In these models, the positions of the electronic orbitals are easily identifiable. In this periodic table, the revealed new features of the elements are illustrated in a new original way. At the end, I would like to express my gratitude to the Omics International Group and the organizing committee for their kind offer to be a keynote and plenary speaker at this international conference.